Welcome back. And on the previous one, I forgot to finish my own question. We're supposed to circle, major, and explain. Here we go. We're actually going to have pretty equal amounts of these two products. And don't put your explanation up there. Put your explanation at the point in the mechanism where you decided you made more of these cations than the others. And your explanation should be talking about this improved cation and this improved cation. Both cations. And don't talk to me about substitution, please. It's not about substitution. When you have a reaction that gets rid of or lowers angle and torsional strains. Remember, torsional strains are caused by eclipsing in small rings. And angle strains are caused by, as the name suggests, bad angles in small rings. And both cations have reduced angle and torsional strains. That's the whole explanation why we would see higher amounts of these two products. You can't say one of these is much better than the other. They're both secondary cations in bigger rings. You might have another rearrangement in a couple of them, but I wouldn't worry about that. I'm not going to do that to you. We're going to do one rearrangement at a time when we're first learning these things. So we have that, and now we're going to move on to a final topic for today, which we will continue on Wednesday. The top reaction is a reaction we saw before. The alkene pi electrons attack, making two carbocations. Very slow because carbocations don't have full octets. Second carbocation even slower because it has less substitution. First is at least tertiary. Bromide ion does its thing. Never hurts to redo mechanisms over and over again. And that was the entire mechanism to make both major and minor products. Now this reaction down here, much faster than above. This reaction happens almost instantly. This one could take minutes to hours depending on your conditions. This one, you drop in a red solution of bromine into the alkene solution, and you'd see the bromine red color disappear almost immediately, within seconds. So why would it be faster than the above one? Or why is the above one much slower than this one? And the reason is the intermediates we're going to generate do not have any octet violations. So that will help. Before we start, though, why did the first reaction start like this? Do you remember? Why did we attack the hydrogen? Why is the alkene pi electrons interested in the hydrogen? And the answer was the hydrogen being bonded to a more electronegative halogen is very positive. So you're saying to yourself, well, that's not going to happen in the reaction underneath. There's no charge here at all. Well, you got to remember, electrons are never sitting still. So at any given time, we could have a temporary dipole. Remember, those are the things that cause London forces. So you already know they exist. But in the next nanosecond, it might shift where this atom becomes positive and this one slightly negative. Or it might be exactly 50-50, in which case the reaction won't happen. The pi electrons are just waiting for one of the bromines to feel positive. And then as soon as that happens, they're attracted to it. And then this reaction looks pretty much like the one at the top of the screen, doesn't it? But it's not. There's something bromine has that hydrogen does not, and they're not showing here. There's 3 of them on the bromine here and 3 of them on the bromine here, and hydrogen has none of them, and bromine has 3 of them. And yes, I think you figured out by now he might be talking about lone pairs. Bromine's got lone pairs. Lone pairs can be used to make bonds. You already knew it right here. Making a bond. Making a bond. Making a bond. Right here. Well, should be the same color, red. And I got a question for you. Why is it coming back to the carbon that has more carbons attached? I want it to be a nicer arrow than that. Coming back to the carbon with more carbons attached. That would be the tertiary carbon. Without this arrow, it would have been a carbocation, right? Like this one. So yeah, I'm going to be making more cation down there than I'm going to be making carbocation up here. This one, it's not as good. So lone pair comes here, and the intermediate you generate, you're going to say, well, that's not a good intermediate at all. It's got a triangle. And I'm going to say, yeah, it's a great intermediate. Watch. So let's just do a triangle. Got a bond to a bromine and a bond to a bromine. You got your ethyl down here. Well, it should be green. The original molecule is green. And you made a bromide. And if you think about it and you do all the charges and things, the bromine had 3 lone pairs. It used 1 to make a bond. There's still 2 lone pairs. So it owns 4 electrons, 5 and 6, compared to the periodic table where it owns 7. Yes, that is a bromine cation. It's called a cyclic bromonium ion. No surprises there. It's in a triangle. It's a bromine with a positive charge. And it's an intermediate. And it has, most importantly, all octets full. That's why this reaction is faster than the one above it. There's no octet violations. You're going to say, okay, but it's got a triangle. That's bad. When was the last time you looked at bromine on the periodic table? 79.9 grams per mole. It's a very large atom. So even though it's a triangle, the bromine's almost wide enough to reach from one carbon to the other and touch them both simultaneously. It's a large atom. So it's not as bad a triangle as you thought. And the next step, which finishes the reaction off and gets rid of 2 charges, gets rid of some angle strain too and some torsional strain. This bromine comes in from 180 degrees away from the other bond to bromine. On which carbon? The more substituted carbon. So we're going to have to talk about this. Came in from 180 degrees away from this. It wanted to be as far away from these electrons as possible, because electrons hate each other. There's a theory based on that. Valence shell electron pairs repel each other. Vsepar. Well, it works for some mechanisms too. Okay, it works for all mechanisms. Keep electrons away from each other when at all possible. That's VSEPR, mechanism version. So I'm not going to come in from the front where the electrons would bump into other electrons. I'm not going to come in from the top back because they're close to each other here. But if from 180 degrees away, they're as far away from those electrons as possible. That's called a backside attack. I'll put it right with that arrow there. Backside attack. And you'll read all about backside attacks before we meet each other again on Wednesday. I think that's a good intro today. You've got enough to digest with all those carbocations. Maybe you want to just review that part of the book, read ahead a little bit about the triangle mechanisms, and we'll continue this discussion on Wednesday. And I hope you have a good day. I'll see you Wednesday.